Hi folks, this is the overview lecture for assignment 19, an introduction to what is a matrix. And so that's our first question I want to look at. What is a matrix? So there's a very simple answer. It's a word that is used to talk about a table of numbers. And I mean a table in the sense of like something you might do in a spreadsheet where you have rows and columns. A more complicated answer is this. A matrix encapsulates a way of transforming vectors, which begs the question then, okay, what is a vector? Now for that, let's pop over to looking at GeoGebra. I've got a GeoGebra, oh, by the way, we're in the computer algebra system version of it, and you're going to want to be in the CAS calculator for really the remainder of the course. So I've put in this command, v equals vector, and you see the argument to that is a list of numbers, 1, 2. And it puts out what the value returns as some braces around a column of numbers, 1 and 2. Now, what it draws in the geometry view is a little arrow, and the arrow goes from the origin to the point 1, 2. So the end point of this arrow is the same thing as the point that's defined by that little list of numbers. But there's a philosophical difference here. A point is just a location. A vector is a way of telling you how to change your location, how to move from one place to another. And in the raw form, a vector tells you how to start at the origin and end up at the point 1, 2. But I could have that same arrow lots of other places on the plane, and it would be the same vector. So where points, you really can't move them, vectors are free to be pushed around, translated. Now I'm going to make a slightly strange and almost pedantic point here, but I want you to realize that an ordinary real number can be thought of in these terms. You can think of it either as a vector or as a matrix, and the context will make it clear. If you think of it as a vector, what you're talking about is a column with one entry. But if you think of it as a matrix, what you're thinking about is a table that has one row and one column. Now, that's often put into shorthand by saying it's 1 by 1. One row, one column. So when I've written the equation 3x equals 12 here, and I want us to think about this as if these were vectors and matrices. This guy is the matrix. It's just a 1 by 1 matrix, but so it's not very exciting, but it's still the thing that acts like a matrix. These other two guys are thought of as vectors when we do this equation. Maybe I could just point that to both of them, so that say vectors. All right, what's going on here? The matrix transforms the vector. So this, when I write 3 times x, it's saying scale the vector x by 3. Make it 3 times as big. And what we're asking here is the question, when I transform x, when is it going to be equal to 12? So we're saying transform this vector and turn it into that vector, and solving that equation is figuring out what the vector x is. It turns out a lot of things can be posed that way, and sort of brilliantly, this matrix notation lets us write stuff like this as if, well, these transformations of many variables as if they were single things. So if you see a thing like this written down, we're going to see things like this written down later. That one's the matrix. They always use capital letters for matrices. And these other two things are the vectors. Vectors in a textbook or something will just have boldface on them. If you're writing by hand, people often put these little arrow type things above them to make it clear that that's a vector. But what a vector x means is a column of numbers or a column of variables, and a vector b would be a column of numbers, and a would be a table. All right, so that's too much information for right now, but maybe come back to thinking about things this way in a later chapter, and it'll help you. So this is the very first page of the combined textbook thing, and again with this crazy page numbering that is sometimes problematic for us. This is on page 206 of the PDF, but it's what's the page number? 41 is the labeled page number. Anyway, what we're looking at right here is actually two matrices. There's a matrix for the year 2014 and another matrix for the year 2015. I kind of wish they had somehow divided these up or put some space between them. But this is a typical example of how a business might use a matrix to hold information. In this instance, this fine furniture company has 3 locations where it's manufacturing stuff. And they're just picking out 2 of their products, chairs and tables. Probably a manufacturing company for furniture would have more than just that. Anyway, in each location, you make a certain number of chairs and a certain number of tables in a year. Suspect also that the numbers would be much bigger, but again, it's kind of a toy example. So this table of numbers here is an encapsulation of the productivity of the company for that year, and it divides things up based on which facility you were making the things in and which product you were making. So the columns indicate different products, the rows indicate different facilities. A total of 6 numbers from that. So when they break these things into matrices, we usually drop all the decorations, the labels on the columns and the rows, and just put these kind of square braces around it. Now, by the way, when we go into GeoGebra, you'll see they use round braces, which is more mathy, but the more usual thing in computers is to use square braces. Well, see how the numbers 30, 18, 20, 12, 16, 10, those are the ones that came from the year 2014. So what are we getting if they do an operation like this? Take the B matrix, the B table, and subtract the entries of the A table. And you see what they're doing in order to make that subtraction happen is you subtract corresponding entries. So we would take, for instance, in the first position up here, the 36 minus the 30 and get 36, you get 6 in the answer. What is that difference telling us? It's telling us how productivity changed across our products and across our production facilities for the company from one year to the next. If instead of subtracting, we added these things, what would that mean? That would say, what's our total productivity across, again, the product lines and across the different production facilities for our company in the sort of combined years? A lot of times businesses will do their the accounting of this kind of stuff on a quarterly basis. So it would make sense to add up 4 such things to figure out the annual productivity. Now this next thing is a little bit less meaningful, I think, in a business capacity. But you could certainly ask questions like, well, what would it mean if we had doubled our production in the year 2014? Well, actually, isn't that 2015? Nope, my notes had it right, 2014. So 2014 times 2, well, that just means take every single number in the table and double it. But that gives you a way to think about it generically. What should I do to multiply a number times a matrix? Multiply every entry in the matrix by that number. Okay, some terminology, and this is, I've already used the terminology. We talk about the entries or the elements of a matrix. Those are the numbers inside the table. The other thing we need to talk about, and I kind of pitched this ahead of time, is how do we discuss the size of a matrix? You should not use the word dimension. If you want, you can say dimensions, because there's going to be 2, right? There's a number of rows and a number of columns. The standard convention is you mention the number of rows first. So like this matrix A, it says it underneath it, it's a 3 by 4. That's because it has 3 rows and 4 columns. This matrix B is 4 by 3 because it has 4 rows and 3 columns. Yeah. One thing I want to point out is it really wouldn't make sense to add up a 3 by 4 and a 4 by 3. Because, well, this would be from a company that had 3 facilities and 4 products, and this would be from apparently a different company that has 4 production facilities with 3 products being produced. It doesn't make sense to do that sort of matrix addition or subtraction. So adding and subtraction is only done when the size of the matrices are identical. Same number of rows, same number of columns. Another little bit of terminology, actually several bits of terminology. Square means what you might think it means. The rows and the column numbers are equal. It is sometimes useful to have a zero matrix. And it's interesting, the zero matrix behaves the way the number 0 behaves. If you add a table of zeros to a table of other numbers, you end up not changing it. So that's what happens when you add 0 to a number. You don't really change it. Now, this next matrix, it's called an identity matrix, is going to be important in the future. But for right now, just know that it's something that got 1s on the diagonal and 0s everywhere else. And those matrices are always square. So you've got a square matrix with this special shape where there's 1s on the diagonal of it. And it's this backslash type diagonal, starting at the 1, 1 position and ending at the 3, 3 position. Ooh, yeah, we've got to talk about that. Does the book talk about the... Yeah. I'm gonna tell you how to label a particular element. Right now my cursor is pointing at a 0 in that 3 by 3 identity matrix. But which particular 0 is it? It's the one in the 2nd row and the 3rd column. So we'd call that the 2, 3 element. This guy would be the 3, 2 element. I get it, they're both zeros, but like that 1 is the 2, 2 element. All right. Vectors, the kinds of things I mentioned get drawn as arrows in GeoGebra, can come in 2 forms. Once you're in the matrix world, you can think about a row vector, which has 1 row and many columns, or you can think about a column vector, and that's actually the usual way we do vectors. If you noticed when we were in GeoGebra, it turned the numbers into a column of things. So usually vectors are thought of as column vectors, but they can be row vectors as well. And the real distinction between those 2 things is only important if you get into physics. So don't need to worry about it now. What about equality? When are 2 tables the same? Well, I feel like that's pretty clear what would happen, right? If you want to say 2 tables are equal to each other, then they've got to be the same size. The number of rows and number of columns have to match, and element by element, they should be equal. Those elements need to be the same. So matrix equality is pretty clear, I suppose. All right, they're showing examples of adding. Now, here we have, let's check out our skills on this. This is a 3 by 3, right? And what is this guy? Oh, also a 3 by 3. They have the same dimensions. So can we find A plus B? You bet. And what are we going to be doing? Well, for instance, the 1, 1 entries in these matrices are a 1 in A and a 2 in B. So we're just adding 1 and 2 and getting 3 in the sum, A plus B. I'm only going to spot check this. How about the bottom right entry? That's the 3, 3 position. It's a 3 in A and it's a 1 in B. 3 and 1 is 4. And that's what you see in the sum AB. Go ahead and verify that every entry in this sum of the 2 tables is actually the sum of the corresponding entries in the summands. C and D, they're asking in part B here, can we do the difference of C minus D? So really we need to check that C and D have the same dimensions. And they do. They're column vectors. They have 3 rows and a single column, each of them. Can we subtract things like that? You got to watch out with subtraction, because if you're subtracting a negative number, you're really adding. And so we'll have 4 minus -2, getting a 6 in that upper position. So what would this be if we turned it into the accounting of a company's productivity? This would be saying we had a single product line, a single column, and 3 different locations where we might be producing that product. So one location made 4 items, another made 2, and the last one made 3. Now, I'm not sure what it would mean for us to be producing -2 items in a facility. I suppose this is a product that facility uses in order to produce something else. But we don't have a something else here, so that's sort of strange. Negative entries can be made sensible, but as we've looked at it so far, not so good. But still, we can do what the operation says to do. Take this table and subtract the entries of this table. So our 2-1 position is going to be 2 minus -3, which is 5. Down there. Oops, I can't highlight it properly. I still can't. So the last spot is 3 minus 4. Okay, I get -1 there. What about A plus D? A is this 3 by 3 thing. D is this 3 by 1 thing. You really can't make sense of adding up matrices of different sizes. So normally people say you just can't do that. Now I want to show you something odd in GeoGebra. By the way, to input a matrix in GeoGebra, there's not a command as there is for the vector. So I'm just going to say M is this matrix. Here's how you do it. Use curly braces to make a list, and the list has lists in it. So we're talking about a list of lists. I'm going to just make up random numbers to put into the list. So curly braces with a bunch of numbers in them, and then those things are stuck inside of other curly braces with commas in between. I'm being boring about how I construct the numbers here. I'm just counting up, but you know, we could put more interesting numbers in there if we wanted to. Okay, hit return. You see what it did? It took my first list of numbers and put them in the first row, my second list of numbers in the second row, and my third list of numbers in the third row. One thing that's a little problematic, I think, with the interface here is if you did this and then you say, oh, wait, I want to change something, you can't do it right on here. It's in a version of things that you can't change. But you can go to the settings and see where the definition of the matrix came from and change that. Like suppose I wanted the last entry to be a 10, not a 9. Boom. I gotta hit return in there, and now over in this picture it's a 10, not a 9. Actually, I wonder if I can do this one thing here. Can I call it M equals? Looks like. And if I just type M, will it respond? Yeah, it will tell me what the matrix M is. All right, so I didn't really kind of want to do that. I was just checking what it was. It understood me. Let me make that other table. What did we call it? Oh, it was, the names were different. I think in the book it was A and D, but I'm going to give this a table that has just 3 numbers in it. Here, well, I guess I'll call it D. And I'm going to put 3, 2, 1. A single column. What does D consist of now? If I have a matrix like that, that's a row of numbers. It's a single row was given as the input. Can we go back to the settings here and see how it was put in? 1 row, so we've only got 1 row. And then 3 columns because there were 3 entries in that row. Okay. Now, what this algebra calculator thing should do if I try to add these things is complain about it, but it doesn't. Well, it complains in a subtle way. It writes this thing on the end. You see, that's never something we've seen before. And I'm not sure what it's trying to say there. But what it did, in fact, was add this row to the very first row from M. And I just disagree with this behavior. This is one way in which I think GeoGebra is doing something misleading. It should say error, I can't do this. But it doesn't. So you're just going to have to filter that by hand. If you go to add or subtract matrices, you really want them to have the same dimensions. And ignore this capacity GeoGebra has to add up things that have different dimensions. Yeah. All right, so what else can we do with matrices? Well, we talked about multiplying by numbers. Let's see what 2 times m looks like. See how it did that? 1, 2, 3 became 2, 4, 6. 4, 5, 6 became 8, 10, 12. Each number in the matrix M got doubled. It's also possible to multiply matrices, but you got to be careful about the order. M times D doesn't work. You see how it said a question mark there? But D times M does. We got numbers out. We got a triple of numbers. We got another matrix out is what we actually got. So I'm going to switch over to the other view and talk about something known as conformability. When can we multiply matrices? Well, there's a short answer to this, which is something that I want us to just practice a little bit. But you'll see why this answer is correct in a second. So what it says is the inner dimensions have to match. And so let me give you an example of that. If you're trying to times a 3 by 4 table with a 4 by 2 table, those 4s, those are the inner dimensions. So when I see this thing, inner means 4 there and the 4 there, and they're equal, so you can do it. This is a matrix multiplication that can be done. Next one I've got is a 2 by 1 times a 2 by 1. They're the same size, which means we could add them, but we can't multiply them because, again, these inner dimensions don't match, right? Those are not equal. So nah, can't do that one. Here's a 3 by 3 times a 3 by 1. Is that doable? Yeah, the 2 3s here and here are the same, and those being the inner things, they match, you can do the product. A 3 by 3 times a 1 by 3, nah. So this one you can, this one nah. So that's a pretty simple rule. You just look at the sizes of the things, and then you figure out what's the what is this actually? It's the number. These inner dimensions. They're the number of columns in the first matrix, but the number of rows in the second matrix. Well, let's examine that a little closer. So we talk about conformability, or a pair of matrices are called conformable, or this way of saying it. A times B is a conformable matrix product. What you need to have is the number of columns in A is equal to the number of rows in B. But I would like us to think of this in a different way. When you have the number of columns in A, that's the length of the rows in A. And when I say the number of rows in B, that part is the length of B's columns. Just maybe real quickly, let's look at a matrix here. I'm going to do 1, 2, 3, 4, 5, 6. Okay. Now that has 3 columns. 1, 2, 3. But do you see how long the rows are? Also 3. It has 2 rows. And now, do you see how long the columns are? They have 2 entries because there are 2 rows. So there's this sort of interchange of number of one thing and length of the other thing. But we're going to really think about the length of the rows in one being equal to the length of the columns in the other. All right, I have to do some miming for you, so I'm going to transition to just looking at me. When you go to multiply two matrices, you're going to do something that's a little bit like the thing where you pat your belly and you rub your head. Rub your belly and pat your head, that's the thing. You have to develop a little bit of physical autonomy between your left hand and your right hand. And so what you're going to do is trace the rows of one matrix at the same time you trace the columns of the other. So rows on one hand, columns on the other. This is my, I hope this doesn't change handedness but this is my left hand. The left hand is going to be tracing rows. The right hand is going to be tracing columns. And when we trace those things in that fashion, we're sequentially looking at corresponding entries in the matrices. We're going to multiply and add up as we go. So you're going to have to learn to trace left hand horizontally, trace right hand vertically, multiply, and keep a running tally as you pass down the entries. I'm going to do a matrix product out for you before I get too much farther in depth of this. But it's important to understand why we would need to go through this rigmarole, because it's a little bit complicated. It's necessary though. So recall the perspective I said before about thinking about an equation like that, 3 times 2 times x equals 24, as matrices, little 1 by 1 matrices, a vector, also 1 by 1, and then equaling another vector that's 1 by 1. All right, well, there are 2 different ways one can parenthesize this product, 3 times 2 times x. You can think of it as 3 times 2 times x, and the other side would be 24. Or you can think of it as 3 times 2 times x equals 24. And in the sort of transforming the vectors way of viewing things, this is saying multiply the 3 and the 2 together and you get a 6, and so 6 times x gives us 24, and it's easy to see that x would need to be 4 for that to happen. But this parenthesization, if you sort of read it as transformations, means first double x, then triple that. And what x value will give you 24 if you first double it and then triple it. This is composing 2 transformations, and this is multiplying 2 numbers. But they have to be the same, right? Because we know the different parenthesizations there don't matter. So this is the point when you have matrices that are being multiplied. Well, I'm going to give you just an example in matrix notation where you'd have a table A and another table B times a vector x equals another vector on the right hand side. The product of A and B has to be the same thing as what you get if you first transform by B and then transform by A. Let me say this in no uncertain terms. Matrix multiplication is what it is, which is going to be a somewhat complicated thing, because the idea of the product of matrices has to match with the idea of composing 2 transformations. All right, so that was mostly just meant as motivation for you. I'm hoping that you'll say, okay, I guess I get it, why there's a reason why I have to learn this difficult thing. And fortunately, you don't have to do it too much, because we can turn to GeoGebra to at least check our work, but you should learn a few times at least. It's sort of a rite of passage. Learn how to multiply 2 matrices, 2 tables of numbers by hand. And once you know how it works and are confident in that, then you can push on and use a computer to do all your matrix multiplying. Here is a matrix product. It's a pretty hairy one to start off with, but I kind of want to show you what's up. So this is, let's check out whether it's conformable, whether we indeed can do the product. Let's see, this first matrix has 3 rows and 4 columns, so it's a 3 by 4. And the second matrix has 4 rows and 2 columns, so it's a 4 by 2. And you see how the inner dimensions match, 4s in both of them. An interesting point, actually, that I elided before, but now you're ready to see this, is that the outer numbers also tell us something. These guys, the 3 and the 2, that's the size of our answer. So when we multiply these things that have rows of length 4 and columns of length 4, the 4's kind of get destroyed and you end up with something that's 3 by 2. Well, okay, so let's do the process. What you're going to do is have one hand trace across the rows of that matrix. I'm doing it with pencils. Why am I doing it with pencils? My fingers will work just fine. I'm going to trace across the rows of the one while I go down the columns of the other. See how that worked? 1, 1 and 1, 2 and 3, 3 and 5, 4 and 7. All right, what we need to do is multiply corresponding entries and then keep a running tally on this. So it's 1 times 1 plus 2 times 3 plus 3 times 5 plus 4 times 7. Well, that was more than I want to do in my head, but let me write down what we just said. 1 times 1 plus, oh, that's in the wrong spot. Under my face. Sorry. 1 times 1 plus 2 times 3 plus 3 times 5 plus 4 times 7. 1 plus 6 is 7, plus 15 is 22, plus 28, I think that's 50. So when we go to write our answer, which is going to be a 3 by 2 thing, we're going to have a 50 in the upper right corner, upper left corner, sorry. Let me do another one of these things. I'm going to stick with the first row of one matrix and the other column, the second column of the other one. So now we'll do 1 times 2 plus 2 times 4 plus 3 times 6 plus 4 times 8. See that pattern of across the row with this finger, down the column with this finger. 4. And what was that product? It was 1 times 2 plus 2 times 4 plus 3 times 6 and 4 times 8. I hope I did this right and I got 50 on that. And we're going to check our work with the computer in a sec, but this is 2 plus 8, 10 so far, plus 18, 28 so far, plus 32, 60. Now, what position am I going to write this 60 in? I was using the first row of that matrix and the second column of that matrix. So this will go in the 1, 2 position in our answer. Remember, the answer was going to be 3 by 2. We've done everything for the columns. That is, we've done everything we can do in the first row. There's only 2 columns. We've done 2 columns worth of stuff. So now we have to do a second and a third row because, again, the answer is going to be 3 by 2. Where does that come from? Again, tracing. But now we trace the second row with the columns of this guy. So 5 times 1 plus 3 times 4 plus 3 times 5 plus 2 times 7. Do I have room to write all that down? Where can I put it? Oh, I've got some space over here later, but I'm going to need to have more of these things. So there's going to be a total of 4 such 4 more computations. I think I'll squeeze them in somehow. What do we just say? The second row of the first matrix, the first column of the second matrix, it's 5 times 1 plus 4 times 3 plus 3 times 5 plus 2 times 7. All right, that's 5, that's 12, 17 so far, plus 15, 32 so far, plus 14, 46. That's what goes here. I got more scrap work to do. Let's see, we need the second row with the second column, and that'll get us our 2-2 entry of the answer. It's 5 times 2, 4 times 4, 3 times 6, 2 times 8. What does that all tally up to? 5 times 2 is 10, 4 times 4 is 16, 26 thus far, then 18 more, 44, and then 16 more, 60. Oh, that's weird. That's 60 again. Is that actually reasonable that the product of first row, second column, and product of second row, second column came out the same? Yeah. Well, look, yeah, there's no reason. That was just a weird chance thing. No rationale behind it. Oh, multiplying things by the last row of our first matrix is going to get easier because it's just 1s and minus 1s. That's nice. So what's our first row, our third row, first column going to be? It's 1 times 1, 1 times 3, minus 1 times 5, minus 1 times 7. So that, let's do it again. 1 times 1 plus 1 times 3 plus minus 1 times 5 plus minus 1 times 7. 1 and 3, that's 4. And these two together are minus 12. 4 minus 12. Sounds like negative 8, doesn't it? Okay, and last position that we need to fill in, that's the third row, second column. So we'll be doing the third row of A and the second column of B. The multipliers in front are these 1s and minus 1s though. So it's 1 times 2 plus 1 times 4 plus minus 1 times 6 and minus 1 times 8. 4 and 2 is 6. All right, well, 2 there, 4 here, 6 so far. And then we're minusing 6, so we're at 0. Okay, it comes out to be minus 8. Another weird coincidence. Let's go put this into GeoGebra and check whether we did it right. All right, I decided I'd save you the pain of watching me enter all the numbers into these things, and I've also tried to blow up the size of things so you can see a little better. For instance, these matrices are never going to be displayed in the graphics view, so more or less eliminated the graphics view. So A is 1, 2, 3, 4, 5, 4, 3, 2, 1, 1, minus 1, minus 1. This is the way that was entered. With, remember the curly braces around the whole thing, and then each row is a list inside of curly braces. And then make sure you have to have commas in between the rows so that we're getting a list of lists. All right, so that's A. B, the lists are of length 2. 1, 2, 3, 4, 5, 6, and 7, 8. Those were the answers. And here is us doing the multiplication. It just understands that if you want to multiply two things in their matrices, it'll do it. Did we do it right? Woo-hoo! I got every single number correct. I was sure I was going to find a typo, or I mean a Braino sort of a addition problem in that, but it worked. I did them all. That was a tough one. for us to start with, but I figure if you've done the harder one, then the easier ones will well, they'll be easy. Let's do one last example, and then we'll call it quits. I'm going to make a matrix, I guess we'll call it C. And I want this to be 1 by 3. So that is, I will have a single row with 3 numbers in it. Just randomly making up numbers. But that's a matrix that we've defined. And then I'm going to make a matrix D. And this has to be conformable with C. So it's going to need to have 3 rows, because C has 3 columns, which is tougher because I'm going to have to make a list of lists where the lists have single entries in them. But how about we put 4 there, and then 1 there, and then how about -2 in the last spot? It needs braces around it. List of lists, but the lists have length 1. What does that do when we get it? We get a column, a single column. So these are 2 vectors, really. This is called a row vector, and this is called a column vector. The reason I wanted you to see what happens with a row vector and a column vector is the multiplying a row times a column is exactly what we were just doing in the rows of one matrix and the columns of the other. C times D is going to give us a number, 13. Okay, check out what that number is. It's 3 times 4 plus 5 times 1, 17 so far, plus 2 times -2, -4. 17 minus 4 is 13. Cool. But look what happens if you do D times C. Can you do D times C? Yeah, those are conformable too. Because now we're talking about a 3 by 1 times a 1 by 3. The 1s are the inner dimensions and they match. And the outer dimensions are both 3s. So we just took 2 1 by whatevers, or whatever by 1s, and created a matrix out of it. A honest to gosh matrix. It's 3 by 3 here. All right, that is it for today. Have a great rest of your day.